Welcome back, guys, to Lesson 2 of Chemical Kinetics here, Chapter 14 of the Tro textbook. In the first lesson, we looked at how a set of individual experiments in which we measured the initial rate while changing concentration of the reactants could provide you a rate law like the one that you're seeing right here in front of you. This rate law is termed a differential rate law because what it looks at specifically is how the rate of change is changing as the concentrations are changing. And what you'll notice here is that it provides you a graph, if you were to graph it, of the instantaneous rate versus any of those concentrations. In calculus terms, some of you that have had some pre-calc or maybe Calc 1 might be staring at that rate and thinking, if I squint my eyes, that looks like something else to me. Namely, if I make the little interval during which I measure the rate as small as I possibly can, what it eventually becomes in calculus terms is this. It becomes a derivative. And when you have an equation that's got the derivative as well as something like bromate, something like the thing that you're monitoring the rate of change of in the same equation, what you have is technically considered a differential equation. Now we're going to switch over to an easier to deal with equation here because the bromide and the H plus in the original one is a bit too much. We're going to come over to the NO2 reaction that we started our discussion on for the next slide. What this rate law allows us to do now, looking at it from this perspective, allows us to integrate it and actually get a mathematical model of how the reaction concentrations will change as time progresses, which remember is usually how we're doing the measurement in the first place. We don't have a rateometer that we're able to hook up to a reaction. We're usually looking at how the amount of stuff I have is decreasing or increasing as time passes. It would be great if we could model that and figure out rate laws that way. And so we're going to look at that with this NO2 reaction because we know that the general form of it is as such. We still haven't figured out what order this reaction is. We're going to try to with our work here today. If I want to turn a differential equation into something relating the concentration and the time themselves, the two things that are on either side of the fraction bar, what I have to do is integrate it. And to do that, I'm going to actually move some things around. So notice that the equation you now see is the result of me multiplying both sides by dt, and dividing both sides by the NO2 concentration raised to this mystery exponent. And so what I wind up with are two individual expressions that I can integrate by essentially treating the derivative itself like it was a fraction. Now, what we get from that is going to vary depending on what exactly the form of this is. But all we're going to do is integrate from the initial conditions to the present conditions. So we're going to say that for NO2, the concentration is going from some initial concentration C0 to its current concentration, which we're just going to call concentration of NO2. Meanwhile, the time is going from t equals 0 to whatever t is now. And if I want an equation that I can just start plugging in random times into, I want to leave that essentially as a variable. And so that's what we're going to do. And I'm going to walk you through this process for a first order reaction. All right, so you'll notice the one difference between the equation you see on my page right now and the one we started with is that this one doesn't have the little n exponent because I'm assuming this is a first order reaction. And we're going to see how this behaves under first order kinetics. And so as I said, we're going to integrate from initial to current conditions. So I'll set up an integral here. And what we'll put over here again is from C0, the initial conditions, and time equals 0, up to current NO2 concentration and current time, whatever those should happen to be. And so my integral of this particular thing, if you've done a little bit of calculus, you may be aware that when I integrate 1 over x, what I end up with is ln of x. And so I'm going to have here now negative ln of NO2 from the final condition minus negative ln of C0. Okay, so again, subtracting final from initial. I'll do the same thing on the other side. It's much simpler here because k is a constant. And so really, I'm just integrating a constant. I wind up then with k times t minus k times 0. And so, of course, that's not going to be equal to anything. doing a little bit of rearrangement here. If I want to solve this specifically for the ln of NO2, what I can do is move this term, which really is plus ln of C naught. I can subtract that from both sides. And that'll give me negative ln of NO2 equals KT minus ln of my initial concentration. From this point forward, it's all algebra. Don't worry, no more calculus. And then I'll just flip the signs on both sides, multiply by -1. And that's going to now give me negative KT plus ln of C naught. And most crucially, what I want you to notice at this juncture is that you're now looking at essentially a y equals mx plus b kind of equation. In other words, looking back at the PowerPoint slide, I can now look at this as something I could graph. If I actually have a first order reaction, I should expect a graph of the natural log of concentration to be linear with time. I expect that I'm going to get a very different look. I'm going to get that sort of curvature that we saw initially just from our kind of suppositions when I look at the just concentration versus time graph. But the ln one should give me a straight line. Going further, if I want to look at just what that concentration versus time graph would look like, well, I'm almost there to begin with. We'll just go ahead and take this entire expression right here and do e to that. So we'd have e to the ln of NO2, e to the negative KT plus ln of C naught. And remembering some of our rules regarding exponents, first off, e and ln undo each other, so this is just NO2 concentration. E to the minus KT plus all that would be the same thing as e to the minus KT times e to the ln C naught, and like we just said, this is just simply C naught. And so what I get is this nice exponential decay, C naught times e to the minus KT being equal to the NO2 concentration at any given moment. As we said before, the form this equation takes is going to depend intimately on what the exponent actually was. So we just saw what happened for 1 over x. Let's take a look at a second order reaction where it's 1 over x squared. Now in this case, when I take the derivative of 1 over x squared, sorry, the integral rather, of 1 over x squared, what I'm going to get is negative 1 over x. And so when that happens, my resulting equation is now going to be 1 over the NO2 concentration minus 1 over C naught. Notice how the new negative that I've brought in by integrating is going to cancel out the one that was there in the first place. And on the right side, again, just like I did before, I still have KT minus K times 0, which just becomes KT. Now, this case is going to mean that a reciprocal NO2 versus time plot would come out linear. So this starts to give us a clue as to how we can take a concentration versus time curve and actually use it to work out what order the reaction is. I can graph each of these possibilities on their own. If I get an ln of NO2 being proportional to time, it's first order. If it's reciprocal NO2 versus time being linear, that means that I end up with second order kinetics. Again, if I want to solve this specifically for NO2, I would add 1 over C naught to both sides, and I would then take the reciprocal of both sides, and here's what we would get. Notice that in this case, I'm going to start with a certain value, 1 over C naught, and then as time passes, the result of this is going to be to make my denominator bigger and bigger and bigger, which means that my NO2 concentration is going to get smaller and smaller and smaller. Similarly, you'll notice that the NO2 reciprocal versus time plot is going to be the only one where KT actually comes out without a negative sign in front of it. You would expect that the reciprocal of my concentration should get bigger as time goes on, because the actual concentration is getting smaller. We'll go ahead and finish this up now for zero order reactions. Those are really straightforward because for zero order, I no longer actually have an NO2 on the left, just the DNO2. And so in this case, what I'm going to get is C naught minus NO2 concentration equals KT. In this case, not terribly surprising if I think about what zero order kinetics would mean. if my NO2 versus T plot is linear, what that means is that changing the concentration of NO2 does not alter the rate of the reaction. It doesn't depend on the NO2 concentration. So I would expect that as I'm destroying the NO2, it will just be a straight line all the way down to 0. That is a rare instance. I'll tell you right now, that is something that frequently happens with, for instance, saturated catalysts, where you have a reaction happening on a surface and you've just run out of room. And so the reaction is happening as fast as it possibly can, adding more stuff, deleting more stuff. None of it is going to speed it up or slow it down. It's just happening as quick as it can on a surface or in a protein. It's a very rare scenario, but when it does happen, you do see this just simple straight line kinetics. And again, if I solve this one, this is probably the easiest of them, I get NO2 equal to C naught minus KT. In other words, I start at C naught, and then for every unit time, I destroy a certain amount of my stuff. And so the first question I have for you, coming back to the reaction we started all of this with the NO2, is this reaction that you see here 0 order? I'll ask you to pause the recording and take a moment to think. All right, now that we've done that, the question I hope has a very obvious answer, which is no, heck no, it is not 0 order. Because if it was, this graph itself would be linear. I would see NO2's concentration just going down in a straight line. We see that there is some dependence on concentration because as I destroy NO2, the reaction slows down. Let's see if we can figure out from the graph what that is. I'm going to put up right here now the data that made these points. And so we have data now for every 50 seconds what the NO2 concentration is. We've already seen, according to the initial NO2 versus time graph, it's definitely not 0 order, but most of us can't really spot the difference between an exponential decay and a hyperbolic reciprocal decay. And so we're going to go ahead and use a little math, and we're going to do what was suggested. If I want to see if this is a first order reaction, I want to graph ln of NO2 versus time. If I want to see if it's second order, I'm going to graph 1 over NO2 versus time. And so just breaking out my handy calculator, I've gone ahead and done this for you guys. Notice, don't be disturbed, the ln's are all negative because I'm dealing with numbers that are smaller than 1. Also for that reason, the reciprocals are all rather large numbers. And so with these numbers, armed with these numbers, we're going to go ahead and do a little bit of graphing and see if we can tell. And from what we see right here, it's a little rough. You might go ahead and take your guess at the moment on which one of those you think is more linear, but I'll tell you this much, if you didn't make the second one, you might talk yourself into the first one, or vice versa. And so let's go ahead and give ourselves a guideline. If we do a linear fit to see what we've got here, the guideline should give us some help. And when we do that, what we observe here is that, yes, indeed, one of these is substantially more linear than the other. Now, you might say the r² values aren't all that different, although 0.999 is very, very close to 1. The thing I'm looking at more than anything is actually the obvious curvature of the first order graph, the ln of concentration versus time plot. Notice that at the edges, it's higher than the line, and in the center it is underneath the line. That's not how random noise in the data collection would look. That's how it looks if there's actually a curve, a bend in your data set. Whereas for the second order one, you might see a point or two that are a little bit above or a little bit below, but there's no real pattern to it. It's just sort of randomly scattered about an otherwise perfect line. And so we would, on the basis of this, declare that this reaction is second order, that it would be K NO2 squared for the rate law, not just simply K times NO2. So in our next video, we're going to look at how this integrated rate law equation allows us to examine things like half-life and actually solve for how a reaction progresses over the course of time.